This next section, continuing Chapter 30 on induction, is Section 30.3. Here we talk about mutual inductance, and a particular aspect that's applied for this is the concept of a transformer. Now, you all know what a transformer is. That's where the squirrel jumps into the transformer and takes your power out when he gets killed by the voltage there. Induction allows for the concept of a transformer which can increase or decrease the AC voltage. Well, in general, when we transmit power and the power lines go across country, we want a very high voltage, maybe even as high as 750,000 volts. The reason for that is the line losses are less with high voltage and low currents. Remember, power depends upon voltage times current. And the losses in the line depend upon how much current is flowing. So it goes as the square of the current. Since V is equal to IR, you can see that this would be R times I squared. So the power loss depends upon I squared. And so therefore it follows that what we want in order to transmit power is to use a high voltage and low current, rather than vice versa. However, such a high voltage is very dangerous. You obviously couldn't bring this into your home. It would arc across normal wires and everything else, and you see the distances that are involved when we have those large power lines and what's required. So this voltage is stepped down, and in fact in your local neighborhood you'll have lines that come around in your local neighborhood from a substation, and these are of the order of about 15,000 volts. Well, when you get to this local distribution of about 15,000 volts, that's still much too high for your house. You want to scale that down again, and the wires that actually come into your house, we're going to be of the order of 250 volts. And that's enough to run your air conditioners, your furnaces, and certain of your major appliances, as well as you can split it into three parts where we have, I should say 240 volts, where we had 120 volts over here and 120 volts over here, or 240 volts over the whole span from the outside here to the outside here, this being the ground wire. And it's connected normally to the ground. This would be 120 volts higher, and this would be 120 volts lower. Well, how do we achieve this? We can achieve that by having a transformer, and a transformer basically will say, let's take a loop of current and let's pass a current through it, and as we pass the current through it, that will create a magnetic field. Magnetic field go through here. According to the right-hand rule, if my thumb goes along here, that says that my fingers would go through the loop, and so I'd have a magnetic field that would go inside. But now if I put another loop right next to that, and I'm going to put this loop kind of on top of it, then when the current through here changes, it'll change the magnetic field through this loop. Therefore, it will induce a voltage here. This voltage will, this voltage therefore will cause a current to flow here, which opposes the original voltage by Lenz's law, as we discussed the other time. And this allows us, by using different numbers of turns here, to raise the voltage up or to lower the voltage. Now, there's an equation for this transformer that says that the voltage here across part 1 versus part 2, that the voltage across part 1 divided by the number of turns we have around part 1 in this loop is equal to the voltage over 2 divided by the number of turns across 2. Now, the reason the number of turns is important because if we have twice as many turns, we will therefore have twice the voltage, that meaning that this is a constant. So we could have like 15,000 volts coming in on here and have 1,000 turns. This would be 15. Well, we're going to have 15 over here, so we can make the voltage anything we want by adjusting the number of turns. If we had one turn, we'd get 15 volts. If we had two turns, we'd have 30 volts. And we can therefore adjust these two numbers of turns to design the transformer like we want. The power that's going to come across that transformer is voltage times current, and that of course is going to be a constant from one side to another also. So we know that V1 I1 is going to be equal to V2 I2, and of course the current is going to be reciprocally proportional therefore to the number of turns. So what kind of problems might you have to work here? Well, simply using this equation right here, you can say if we started out with 15,000 volts here, and we had, as in my example, 1,000 turns, then that would equal to what would we have over here if we had 100 turns. So this would be V1 and N1, this would be V2, and this would be N2. Well, you can solve this in your head. 1,000 into 15,000 would give us 15, and that 15 times 100 would be voltage 2 would be equal to 1500. It would be 1,500 volts. And that would be the output from this type of transformer. Okay, that's too high to go into your house. You're going to need a little bit less than that, so you'd have to adjust this. And we could say if we wanted a voltage of exactly 240 volts to come into the house, how many turns would we have to have? And in that case, you'd put 240 right here and solve for the number of turns that was required. Again, also, power that comes in is the power that goes out. This is energy conservation. Remember, this only works for alternating currents, because if this current is not alternating but just fixed, then we're not going to have any changing magnetic field, so no current's going to come out over here except when we're starting this thing up. So the virtue of alternating current, or AC, is the fact that we can easily step up the voltage or step down the voltage using transformers. Okay, that completes section 30.3.